All right, now it's 9:01. Let's get started. So, okay, what is confidence interval and when do you use it? Someone answer?
So confidence intervals, they show us the likely range of values of the population mean, and we will use it when we are trying to estimate a population parameter such as population mean or standard deviation.
Okay, so basically your answer is it is the likely range of a population mean. Okay, so this is the first part. In a way, it's correct. The correct part is the likely range. Okay, but what happens is it may not be the population mean. Okay, it can be any parameter. Okay, because it can be, for example, the likely range of let's say the standard deviation, or it can be the likely range of the, when you do about correlation, it can be a likely range on the correlation coefficient. So it can be a likely range of everything, anything, basically. Okay. So when you have likely range,
Yes,
all right. So when you have likely range, you have to then tell me how likely. So this you have to give a percentage. So how likely is something to happen? Now, one thing to take note of confidence. So this is exactly when do you use it, when you want to provide a likely range of a parameter. Okay. So in all, for confidence interval, there's actually two components. One is the eraser. One is the likelihood, which is the percentage. Another one is the range. So these are the two things. Okay. Having said that, there's actually a few other components to take note of. One is the more confident you are, the larger the range. Okay. This is always what will happen. The more confident you are, the larger the range. Okay. But can we be too confident?
Yes.
Okay. When we are actually too confident, it means that the range is so large that it's actually quite useless for us. That's what it means by too confident. Okay. So let me just give you two statements. Let's say at the end of the semester, you come and ask me, and I give you two statements. Basically, what is the average class grades? Okay. So my first statement is, I'll say that I am 100% confident that the class average is between 0 and 100. Okay. Second statement is, I am, let's say, 70% confident that the class average is between 65 and 80. Now, both of them contains the same information. but which statement is more useful to you? Which statement is more useful to you? Ding, which statement is more useful to you? Ding, are you there?
Yeah.
Yeah. Yes. Statement 1 or statement 2?
Uh, Statement 2.
Statement 2, right? Yeah. Obviously, statement 2 is more useful. Because statement 1 is, yeah, you already know, because your average marks will definitely be between 0 and 100. So statement 1 is actually oxymoronic. Okay. If I want to be more confident, I have to expand the range, essentially. So if I will say that, okay, you say that 95, 65 to 80 is too wide. If I want to reduce this range, automatically I reduce the confidence. Okay. So it is a trade-off between how confident you want and the range that you can accept. Okay. So this is how confidence interval work. And how do you get this range versus the confidence? Is using your statistics. The two distribution that you use is your, so this confidence, right, will be some average plus minus a gap. Okay, this is some average plus minus a gap. So this gap is determined by a distribution and a standard deviation. This distribution usually comes from two different distribution. One is your normal distribution, one is your t-distribution. When do you use a normal distribution? When do you use a t-distribution? Is dependent on sample size. Okay, and the confidence level that you have is actually the area under this distribution. Make sense? Okay, so if I were to erase all this, whether is it normal distribution or t-distribution, it doesn't really matter. Okay, this can be t or this can be z value. So this is the average. Okay. You will always find that the confidence interval plus minus gap, it means that it is actually symmetrical. This gap is symmetrical. So I can say that I am maybe 60% confident. So if I'm 60% confident, that means this area here will be 60%. So what is my value at this lower and upper range? Lower and upper range. Okay. If I want to be more confident, I will expand this and I go to, let's say, 90% confident. I keep expanding the range on both sides. Okay. This is why when I go to 100% confident, I will cover from negative infinity to positive infinity. If 100% confidence, I mean, I'm talking about the whole area under the curve, which is actually quite useless. That means it's all the probabilities. All right. So these are the few things that you have to take note of. Okay? And confidence intervals can be quite useful for us to determine a lot of things. Okay? We use confidence interval for many things. Like for example, we use it. What is the likelihood that something breaks down between some months and some months? Okay. So this, what is that maybe your watch or your laptop breaks down between 36 months and 48 months. So using this type of information, I can construct your warranty period. Okay, just by you have done this before in the last few tutorials. Okay, so it's actually confidence interval is the using a different way to look at the same problem. So having said that, we will not go through all the questions because like all those highlighted in red, like question 4 and question 5, they are more theoretical. So we will not bother about them for your BDA lessons. But if you're interested, then you can go and read up. This is to tell you to read up about more the theoretical basis of stuff. Okay. So then let's start with our questions. Okay. So what is the difference between confidence interval and a hypothesis testing? Felicia?
Confidence intervals use data from the sample to estimate a population parameter, whereas like a hypothesis test use data from a sample to test a specified hypothesis.
Okay. All right. So confidence interval is actually provide you with a range of likely data. So it's provide a range of a parameter. Okay. This likely data is actually from a parameter. Okay, that's correct. Hypothesis testing. Again, what was your answer for hypothesis testing?
Um, use data from a sample to test a specified hypothesis.
Okay, good. Yeah lah, test a specified hypothesis. Okay. So this actually gives you a yes or no answer. Okay, so it's a binary outcome of whether does it tell you, give you a yes or no answer, but it doesn't give you the range. Okay. So hypothesis testing is very controlled by the significance level. It just tells you within a significance level, is it likely or not likely to happen? It doesn't tell you the range of the data itself. Okay. So that this is a major difference. So what is the best interpretation of 95% confidence interval for the mean? Yeah, Ihan.
It means that we are 95% confident that the interval contains the true population mean.
Confident that the interval contains the true population mean. Correct. This is right. Okay. The critical word here is this word must be confidence. It's not chance. Okay. This is in one of the slide called the common misinterpretation of something of confidence interval, I think. So this confidence interval means that okay, the interval contains you're 95% confident that the interval contains the true population mean. Now we never actually know what is the true population mean. That is why we have to use a confidence to estimate what is the true population mean. Another way that you will look at it, some people will use a more frequentistic point of view and say that if you take repeated samples, okay, that means multiple samples, okay, and you calculate the 95% confidence interval for each sample. Okay. 95% will contain the true population mean. Okay. What does this mean on a graphical point? Okay. Let's say that this is the true population mean, okay, or any variable. Now, you can take one sample and then you construct a 95% confidence interval. So let's say these are from sample 1, you construct a 95% confidence interval, it comes to this range. Okay. Sample 2, you construct a confidence interval, it will come to this range. Sample 3, construct a confidence interval, maybe it will be this range. Sample 4, and it will be this range. Sample 5, maybe this range. Sample 6, here, and so on and so forth. Okay. But you are quite sure that if you construct maybe 200 samples and then you construct confidence interval for each one, out of these 200, 95%, that means 190 intervals will contain the true population mean. Okay. For example, this guy contains a true population mean. This guy contains a true population mean. This no. This yes. This no. This yes. So you have 95% of the ticks that contains a true population mean. So this is, you will commonly see, is another way of interpretation. Okay. So this is what we call as a more of a frequentistic point of view. Any issue with this concept? Anyone? Okay. Okay, so while we are at that, I may as well just show you another concept. Now, if, for example, the 95%, if let's say you do your, okay, 95% of the, what am I trying to say? Okay. Let's say you have a data, okay, and then your hypothesis is that the average of the data, or rather, in this case, I should use the mean. The average, the mean is equals to 0. Alternate hypothesis is the mean is not equals to 0. Okay, so your data you calculate, you can calculate the average and the standard error. Correct? Using the average and standard error, you can produce the 95% confidence interval of the mean. So you have write this as some value and some value. Okay, any problem so far? This is what you done in the, today is tutorial 7, you done in tutorial 6 and tutorial 5. Okay, so you have confidence interval. But however, should these two numbers, if the range, or if the confidence interval includes 0, automatically you will accept the null hypothesis. Okay, if accept the null hypothesis at 95% confidence interval, confidence, or 5% significance, or 95% significance. Okay, if the range excludes 0. Okay, so for example, it can be from 0.5 to maybe 1.2. So excludes 0. Then you reject the null hypothesis. Okay, this is how confidence interval and meets with your hypothesis testing. Because there's some software that uses confidence interval to test your hypothesis. Yes, okay. Some software like Minitab, which you never used before, use confidence interval to test your hypothesis. So it's actually doable. Okay, so it's actually confidence interval and hypothesis testing is like the two sides of the same coin. You have to get familiarized with it. Okay. So let's say, for example, if I calculate my number is maybe 0.1 all the way to 0.9. So probably there is some chance that 0 is actually in the boundary. That's why I cannot reject the null hypothesis. If you plot it on a graph, it means that this is the average, but your confidence interval will go from -1, minus 0.1, all the way to 0.9. Okay. So your 0 will be here. It will not be in the critical region because this is the non-critical region. It's the opposite now. Okay. So this concept, when you have time, please sit down and slowly work yourself through, argue yourself through. It can be quite useful for you in future. All right, so let's get to the actual calculations now. Okay, so we have random sample of 70 Singaporeans surveyed for the number of hours they sleep. So they yield, so first 70 Singaporeans, important. Average of 7.1, standard deviation of 3.3. So find the 95% confidence interval. Okay, so let's just get your answer and see whether you have your answer. So, Konara, why don't you give us all the three of them and see whether, at least give us the first one.
Mu is greater than 6.45 and less than 7.75.
Hold on. Where is, hold on. This is, yep, 6.45. Okay, and 7.75, correct. Okay, now, because you use a normal Z table or T table.
I use T.
That means you use your normal distribution or T distribution.
T distribution.
You use T distribution. Okay. Now you realize that you use T distribution, you will still get something very similar. Although if it's more than 30, you can use your Z distribution table. But because when it is more than 30, T and Z becomes very close. So you will end up with maybe like the third or fourth decimal place different. Okay. But you still get the correct answer in that sense. Okay. All right. So this, by right, you should use the Z distribution because it's more than 70. Okay, under central limits theorem. But if you use a T distribution, the error is not going to be very large. It will actually give you the same answer to the third significant figures. That's fine. Okay. So how about 6B, Konara?
Greater than 6.33, less than 7.87.
Yep. Correct. 7 point what?
87.
87. Yeah. So if you use a T distribution, T distribution or Z distribution, it will give you the same answer because it's close enough. Okay. How about 99%?
Greater than 6.09, less than 8.11.
Okay, 8.11. Actually, this if you get nearly 8.2 because, but we are still all right with it. The answer is supposed to be 8.2 because you kind of use a different distribution. It's close enough. Right? Now, based on this, what can you infer when look at this number, the interval, the confidence level versus the interval. So what can you deduce from these three answers?
As the significance level increase, the range becomes wider.
Yeah, as the significance level, or basically the confidence level increases, range becomes wider. Okay, so basically that's what it means. So can you actually have 100% confidence? Do you think you can have 100% confidence? So let's try. Okay, Hugh, why not you just think about this? If this question is changed to 100% confidence, what will be the range be?
The range should be nil. There won't be any range.
There won't be any range.
It'll be extremely small because maybe 100%.
100%, you see?
It'll be very wide. It'll be very
Very
wide,
wide,
but
right?
because
So
I'm just kind
90%.
of going with 7 because the z and the trying to figure out what number we can put for the z diagram to. But basically, because 100%, there's not really anything I could put there. So we just put get. I don't know. That's kind of what I got in the end. So
Yes. So 100%, it is not calculatable using your distribution, correct? Because in your distribution, there is no 100%. Okay, it will be a very wide range. If you look at this range, right, at 90%, the width, if you take this 7.75 minus 6.45, you get the width of 1.3. Okay, here you get the width of 1.54. Here you get the width of 2.04. This is why Konara said that the more significant or the more confident you are, the wider the range, the range actually increases. So 100% confidence interval, there is actually the width technically becomes infinite. Okay, for a very simple reason, because your normal distribution never touches, the line never touches the axis. So you cannot know what's 100%. However, we can actually infer the 100% conceptually. I can say that 100% confident that the mean hours will be between 0 hours and 24 hours. This is conceptually, because that is the length of a day. All the values have to fall underneath it. Okay, so this is a kind of a trick. Okay, but that's why we always never use 100%. And based on this concept, we also never say that when we do a hypothesis testing, especially using Excel and so on, right? We never say that the p-value equals to 0. Okay? This is very wrong. Okay? Sometimes when you do your hypothesis testing, your t-test, everything, right? You can have p-value near to 0. Okay? But that is a very wrong thing. So you have to find out for each software, what is the limit of the p-value in Excel. When the p-value gives you 0.000, it really means that the p-value is actually lesser than 1 you are using the latest version of Excel, 1 times 10 to the power of minus 240. Okay, never write p-value equals to 0. When you go to university, you will find that this is a serious problem. I've seen people fail the whole exam because they write p-value equals to 0. The professor just doesn't mark the rest of the paper. Okay. If you put p-value equals to 0, in chemistry terms, is as wrong as you are saying that acid has high pH. It is as wrong as this. All right. So obviously this is wrong. Okay. Now, okay, so question number 7. Assume the file contains a population mean, of the schooling age, number of years of schooling is corrupted. You only show the population variance. Okay, take note this variance and the sample. Okay, so construct the 95% confidence interval. Okay. Oh, I missed Benjamin. Wait, is your mic okay already? Or your mic is still dead? Okay, so I think Weiqi's mic is still dead. All right, Benjamin. Number 7.
Yeah. Mu is greater than 8.48 but lesser than 11.5.
Okay, but lesser than 11.5. Okay, correct. So this answer, what is the assumption that you have made?
That one I'm not too sure. Is it like the distribution of the sample mean is normally distributed?
Correct. So confidence interval have to assume that the data is normally distributed. Okay. If the data is not normally distributed, you cannot construct confidence interval the way we do it. Okay, let's say for example, if the data is this type of distribution, can you construct and then the data is this distribution, right? Your mean will be somewhere here. Okay. How do you construct the confidence interval of the data? That means the value of x falls under a certain range. So you'll be between here and maybe here. It is no longer a equidistance for the gap. So you cannot construct a regular confidence interval. Okay. And even for population variance, all this, right? Variance is dependent on normal distribution. Okay. Okay. Calculation wise, do you have anyone have any problem? Okay. Oops, what am I doing? So question number 8. Tracy.
Mu is
Okay.
lesser.
Okay, before mu, do you use t distribution or normal distribution now? Z
T
table or T table?
distribution.
T table. Okay. T is because 20. Okay. All right. So your answer?
Mu is greater than 472 but lesser than 486.
Okay. 486, correct. So all of you should get this answer. Yep. Okay. Okay. So the main part is you have to know how to calculate using the variance and the standard deviation. Okay. So in here is what you have. You have the mean first. So mean is 479. Okay. So 479 plus minus the from t distribution, you get interval of 2.861 times the variance, which is 131, divide by the sample size, which is 20. Okay. So this is where you get this number. Okay. So question, let me just get it out. Question 9. Okay, Maximus. Question 9A.
How do I give you the
Maximus, you are a bit too soft today.
what do I need to give?
I don't know, you have to scream louder at your computer.
I think
Okay, how about this? If you can't...
Sorry.
Okay, now it's better. Yep, okay.
Yeah.
So for part A, 90% confidence interval.
I got 106.6
Uh-huh.
less than mu
Mm-hmm.
less than 107.4.
107.4. Okay, a little bit wrong. So what distribution you use? T distribution or normal distribution? T table or Z table?
I use normal.
Normal. Okay, so 50, you should use normal. Okay. So what you have is to get, maybe my answer is because you get to the okay. So 90% confidence, you should get here 107, which is the average, plus minus, here's 90% is 1.65 times variance is 30, 35, and population, the sample is 50. So do you get this? Use this.
I think I use a Z. The Z value. I didn't get 1.65 that part.
You didn't get 1.65.
Yeah.
So what number do you use here?
I got 0.5. I refer to the Z table, I think.
You get 0.5.
Yeah.
Okay. So 0.5. Okay. So you refer to a Z table. Let's see. Oh, I got to hunt down the Z table now. Okay, formula. Okay, so this is the Z table. Now, what you want is the area. That means this area, if it's 90, right, those in the center should be 90%, which means that here will be 10%, here will be 10%. So then you look for the 0.1, 0.1, which is 0.1, where is 0.1? 0.1. You get 1.5. How do you get 0.5? Oh, no. So 10%, 90%. So 10% here, you should get each one to be, the area have to be, here will have to be 5%, because 5% on both sides add up to 100%. Okay. So you need to find the 0.05 in the table. So 0.05, you end up with 1.64 and 1.65. We use the one that is more so that it's actually a little bit lesser than 5%.
Yeah.
This is the one to get 1.65. . . 65.
1.65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65. 65.
You understand how to see this table?
Yeah, I understand.
Okay. Yeah.
Yeah,
So
so
I think you read the table slightly wrong. Okay. So this is where you get. Okay. The answer is actually very close because my answer is actually 108. So you just missed by a little bit, which is fine, not too bad. The main thing is know how to calculate. Okay. Because in Excel, if you have the data and then you generate, right? Excel actually generate the confidence interval for you. So you will almost never get an error. Okay. However, it turns out that the data is inaccurate as only 27 of the students provide the correct data. Okay. So the other students can be spent too much on their phone and all this. Okay, so this is a very classical case. When you do any form of surveys in future, you have to check whether is the data properly collected. Okay, so this is dealing with survey questions. You have to check with data whether is it properly collected or not. So I'm sure you have seen cases where data is not properly collected and will mess up all your readings. Okay, so how do you construct a 95% confidence interval now, given that the sample mean and variance is 91 and 22? So the n now becomes 27. So what will be your answer, Maximus?
89.144 less than mu, less than 92,
Less than
92.856.
92.85, right? Yes. So this you got it right already. Okay. Okay, so let me just ask you a simple question, but this applies to more of the food science people. Okay, let's say when you want to do testing, sensory test, how do you ensure that your testers are correct? Okay, let's say you have a person testing. This is your let's say your friend. Okay, you ask him to drink 5 cups of orange juice. Okay, and ask him to rate them from 1 to 5. How does he find each orange juice? Okay, how do you test your friend that he is accurate? That means his tongue is good enough. His or her tongue is good enough. So this is A, B, C, D, E. Okay, and then for example, he gives maybe this is 2, this is 2, this is 4, this is 3, this is he likes this juice a lot, so this he gives 5 ratings. So these are ratings. How do you test that your friend is doing a good job?
So could we use a could we use a sensitivity test?
Sensitivity test in how? You can. I'm asking you how to test it. Sure. How do you test it?
So based on the ratings given for each of the different food samples A, B, C, D, etc. So if there's a higher rating given, then it implies that the person enjoys that particular sample of food more as compared to the rest.
Yes, it's correct. So your friend probably, let's say if this is Max, Max probably love food number E or did drink number E. But how do you know that Max is a reliable tester? How can you trust Max reliability?
So perhaps another party should also be use to give ratings for each of the food samples, sir?
Yes, you can do that. You can do that, but the problem is you are testing Mac's mouth. For lack of a better word, you're testing his tongue. How do you know that his tongue is actually testing correctly? Okay. So if you get another friend to test, you are actually assuming that the other friend knows Mac's mouth pretty well, which is may not be the case. So how I will actually do this experiment is, I will, let's say I want to do 5 orange juice. What I will do is, I will actually give Max 8 items to test. So I will give Max another few items. I'll give you 8 items. But just that these items are replicates. So I can give him item number B, item number D, and item number E again. I can randomize it. And hopefully, if his tongue is sensitive enough, he should give me this result. Correct? The first and second time, that means he doesn't know that I'm giving him only 5 things to test. He thought that I'm giving him 8 things to test. But the 2 of the same sample should give me the same result. Okay,
Yes,
so this is how you test Max. Okay. However, if Max actually comes out to a situation, whereby you give him the same sample, and now he decides that, okay, originally he gave this as 4. D, he give it as 1, and 5. E, the second time he give it as 1. Then you know that Max is actually not a very reliable tester, because he just, for the same drink, he gives you totally two different answers. One time very good, one time very poor. Of course, this has a lot of other parameters. For example, certain food, if you eat very sweet food, the second time you eat it is very horrible.
Yes, sir.
Okay, so you can actually test it this way. So this is usually what, for the food science student, they are doing food sensory testing. They need more than what they are testing for. So it can be quite useful. Okay. So this is for you to think about. Okay, so let's look at question 10. Okay. Now, again, back to this Max story, right? This is quite useful because think about it, when one of the work that I used to do is to do DNA fingerprinting. Okay. I do DNA fingerprinting. How to spell finger? Fingerprinting. Okay. So now you have a marker band and so on. So you have sample 1, sample 2, and DNA fingerprinting, especially using your PCR-based fingerprinting, right? Some of the very faint bands, you have to deduce whether the faint bands are there or not. So we actually take the same sample. That means, let's say this photo, give, let's say, Max on today. Ask him to get me all the bands that from sample 1. Okay. 5 days later, I can give Max the same photo and ask him to do sample 1 again. I check his reliability that way. Because sometimes for PCR, especially on gels, you start to imagine bands. So that is how you do iterator reliability. You check your own self. Okay, so this can be quite useful. All right. Now, question 10. Let's have the next one, which is Akil. Question 10A. Confidence interval of the true mean of acetone.
21.67 less than mu less than
21.7? 67.
67
less
than mu less than 22.33.
All right. Okay. So found that mean, yes. So this is how you actually test the acetone. Okay. Basically, how do you test, let's say, the 95% confidence interval for your instant noodles or your cup of others ice cream? what do you think happened to the width if the interval is actually increased to 95%?
The width becomes wider.
Yeah, width becomes wider. No? Correct. Width becomes wider. Okay. So the company labeled that the acetone is 20 ml. Is this reliable based on 95%? 90% confidence?
No, it's not, because the amount of acetone has to be more than 21.67
Correct. No, because
ml.
the amount of acetone is kind of between 21.67 ml to 22.33 ml. Okay, so this depends a bit on what you want it to be. Okay, so let's say, will you? Then if I ask you another question, will you be happy if this is the actual result in your experiment? That means you want to buy 20 ml of acetone, but the actual acetone amount that you have for the same price is between 21.67 ml to 22.33 ml. Will you be happy?
Yes.
Yes, okay. It does depends, okay? It does really depends. If this is your ice cream, that means you go to McDonald's and you buy your ice cream cone. So McDonald's say that one ice cream cone is 70 grams of ice cream. And you want to do your statistics and you buy 10 cones to try. And you find that your 90% confidence interval is actually 72 grams to maybe 76 grams. I think you'll be quite happy, right? You get 2 to 6 grams more. Right?
Yeah.
Will you violently object?
No.
No, right? But if this is medication, then you have a problem. Medication needs to be exact. Okay. So what happens is, let's say, if I ask you to pipette 100 microliters of water, okay, and in reality, every time your pipetting skills is a bit off, and your 90% confidence interval is actually, let's say, 102 to 106 microliter, will that be a problem?
Yes.
Yes, correct. So it plays both ways. Depends on whether you want to be more or you want to be exact. Okay, so this can be quite useful for a lot of different testing. In fact, I'm sure for your first year practical, you have pipette water already, right? And to weigh the water and see how much you pipette. So this is also how you calibrate your instrument, whether your instrument needs further calibration. Okay, we will not go through 11 and 12 because they are more theoretical as well. So let's go through 13. And that is the last one. Okay, Mr. Heiko. Heiko, are you awake?
Oh, yeah.
Yeah, okay. So what happens here? What is the 95%, 99% confidence interval?
Oh, I'm not sure actually.
Not sure. Okay.
Yeah.
So this is because you're not, this is not an easy question because you are testing proportion. Okay. The proportion is actually 0.4. But what you are trying to estimate is the confidence interval for this proportion. Okay. Correct. So 40% wants fewer advertisement. So what is the proportion? That means it is 40% plus minus what range? Now, this is where you have to go to the lecture. In fact, this is actually in your lecture. PowerPoint. This is lecture what? Lecture 7, right?
Yes, sir.
Okay. So lecture 7, you go all the way to the last slide. You use this. So proportion, you actually use this to calculate. So what you have is 0.4 plus minus 1,600 readers. Okay, so 1,600 readers, 0.99. You can use your Z table. Okay, and 0.99, which means that the alpha will be 0.005. Okay, so let's go to the table. So this region, what we need is 0.005. Okay, so we find 0.005. Where on earth do we get? 001, 004, 0047, 005, 005 will be here. Okay, so we always take the lower one, which is, in this case, 2.58. Okay, so where am I? Okay, so this is 2.58. Okay, then we multiply by what is shown here. Okay, so it's P1 minus P over N. Okay, so it is the square root of P1 minus P divided by N. Okay, so here we end up with 0.4 plus minus 2.58. Okay, P is given here, so 0.4. 1 minus P is 0.6. Divide by N is 1600. So then you will put it back here, calculate this, put it back here, and you get an interval of 0.368 and 0.432. Okay, so you are 99% confident that, in this case, you are 99% confident that between 36.8% to 43.2% of the readers prefer fewer advertisements. Okay. Michael, do you manage to know what am I doing? What I'm doing or what am I doing?
Yeah.
Okay, so this is how you do it. Okay, so out of the whole thing, right, this slide is actually more useful. This is the most useful slide. The last slide is the most useful slide. The rest of it is teaching you the concept and the theory and how examples. At the end of the day, this is a slide. Please remember it, copy it down somewhere, put it inside a logbook or whatever thing. Okay. Remember the first few lecture we do odds ratio. You can also do confidence interval for the odds ratio. Okay, so it's quite useful this way. Okay, so let's go back and do our true false questions. Okay, hold on. Let me just get my true false questions out. Okay, so Sean, you have answered a bit too many questions already, so I shall skip you. Give others a chance. Okay, Ranjini, 1A.
I put true.
True, correct. True, okay. You're finding 95% confidence interval of the population mean. The increase in the sample size will decrease in the width of confidence interval, correct? Because if you are using your t distribution, you'll find that the the width is actually reduced. Okay, that's true. Okay, Danielle, for question B.
True.
True, correct. Okay, the width of the confidence interval is affected by sample size. So if you get the first one true, second one, you actually know what's happening. Okay, larger sample size actually means smaller confidence interval. Okay, there, Jeremiah. Question C.
True.
Okay, no. You never halve the population size. Okay, you halve the width. Okay, to halve the width of confidence interval. Okay, this part is technically totally wrong. So this is false. Okay, so don't do that. If you need to find the confidence interval, to halve the width of the confidence interval, that means if you want to, let's say your confidence interval is from 5 to 10. To halve this width, you cannot halve the sample size. It's dependent on the confidence itself to halve it. You can have to reduce this confidence to halve it. Never halve the sample size. Okay, please take note of this. So this true false question quick checks is actually for you to know where is a fundamental error in your understanding. Okay, which is good because since we caught it now, don't ever do that. Got it, Jeremiah?
Yep, thank you.
Okay, good. Okay, Hui Ping, next one.
False.
False, correct, false. Because it's not always just a mean. We have technically calculated confidence interval for proportions, for even odds ratio if you really want to. So obviously it's false. Okay, question E, Jia En.
True.
True. Okay, let's see. The statement 95% confidence for the population mean is equivalent to probability. Okay, this is false because confidence interval is not probability. Remember when we go on, I actually say that the word confidence interval is actually important. Confidence interval is not the same as probability. It's not the same as chance. So this is a subtle language issue, which if you actually have to spend a lot of time trying to figure out this misinterpretation, especially the first one. Okay, so this is also be very careful with how you write your statements. Okay, so this is false because chance means probability, and it's actually given here that this is a misconception. It is not the chance because why? The true population mean is not a random variable, it's a fixed number. Okay, so you get this, Jian? Okay, good. Okay, so any problems for today?
Sir, may I ask, with regard to question 6A.
6A, let me go 6A, okay?
So for such confidence interval questions, is it correct to say that we will always be making use of a normal distribution like X follow, and we will always use this sort of formula for doing confidence interval questions, sir?
Okay, so the assumption, yes and no. The assumption here is that the data is normally distributed. If the data is normally distributed, then yes, you can follow the same formula. Although you may have to decide whether you want to use the T, Z table or T table. But if the data is not normally distributed, the way that you're calculating cannot work.
Yes, sir. Is it also correct to say that when we are using the formula x follow and then we will have the mean, then comma the variance divided by the sample size? So the part about the variance divided by the sample size is something like the equivalent of the formula x follow n then mu comma sigma square. It's something equivalent to.
Now,
Uh,
what you're saying is you write this, for example, your data is n, and then this is your mu, and then this is your variance, correct?
yes, for the normal standard normal distributions.
So usually, right, my advice is try not to write this. It is it's easy to get wrong. You just say that, write in words, the data with mean of what and standard deviation or variance of what follows a normal distribution. Write out in words. Okay? Because this is not easy to understand. Most of you are not mathematicians. It's not easy to understand because what you need is a variance here. You will end up writing n is the mean and the standard deviation, which is wrong. Okay? It has to be variance. So this is wrong. When the standard deviation, it also means that the mean and the next one, right, is you want to calculate the mean, right? This can be your standard error. The variance of your standard error. It's not standard error itself. So that's why you write it out in words. It's much safer.
Yes, sir.
Okay.
So also regarding the final part of question 6 about the inference about the confidence interval when the significance level is increased. So alternatively, can we say that the higher the level of significance, then the smaller the range of the two set values associated with the confidence interval, sir?
Okay, significance, as you realize, in fact, I'm trying to avoid this question. Significance, as you realize from the last two tutorials, even this tutorial, right, it can be a bit misleading. Because sometimes you use 5% significance, sometimes you use 95% significance to represent the same thing, correct? If you never,
Yes.
yeah. So this is why I try to avoid significance level when I can use confidence interval.
So meaning that we don't make any mention about significance level, we just talk about how the confidence
Interval and the width. Think about ways of making your sentence clearer and less easy for people to misunderstand. Okay? Because right, if you look at previous questions, sometimes certain questions ask you to test at 5% significance level. Sometimes certain questions ask you to test at 95% significance level or 95% confidence. These two actually means the same thing, but it is very easy to mistake the significance part. It is a classical problem. You'll see some textbooks actually even do flip-flop all the time. This is why if you can use the word confidence interval and it helps you make your life easier, don't use the word significance. Okay.
Yes,
Here, this is why I call significance level and confidence interval to be synonymous with in this context.
Yes, sir. I see now. So also, like at the end of such confidence interval questions, so is it necessary to include like the part saying therefore we are, for example, 99% confident that the true value of mu lies between this value and that value?
Yes, you should. You should, because at the end of the day, you are a biologist. You are not a mathematician. So don't end your question with just a number. End your question with a conclusion, a conclusion that you can tell, you can write into a report. Okay, so that's important.
Yes, sir. Yes, sir.
Okay.
So also for question 8, for the final answer about the range, so just to clarify, shouldn't the range actually be 395.2?
Question what?
Question 8, sir.
Question
Uh,
8.
uh,
This?
yes, sir. Meaning that the mu is greater than 395.2, but is lesser than 562.7, sir. I mean, after we did the
No. How do you get that? Because
so,
what,
so
what, what, what is this equation that you use?
So I use to get the lower range, I use 479 minus 2.861. Then the 2.861 was multiplied by the square root of 131 divided by 20.
Okay. 131 divided by 20.
No, sorry. 131 divided by the square root of 20, sir. Not square root of 131 divided by 20.
So you actually take minus
One.
2.861 times 131 divided by square root of 20.
Yes, sir.
Okay, no, you can't do that because this is variance. And when you calculate it, you need if you're doing this, you're assuming that 131 is actually the standard deviation. So it's wrong.
Oh.
Yeah. So by right, you're supposed to take here 479 plus minus 2.861 multiply by square root of 131 divided by square root of 20. Because from your standard error, you use your standard deviation divided by square root of n. Okay, but here it gives you the variance. So from variance to get to standard deviation, you square root this. That's why you end up with square root on both sides. So in this case, you add up these two together because what you're given is this guy and this guy. So you end up, put it together, you end up with standard error is your square root of variance over square root of sample size, which is this.
Yes, sir. I understand now. Thank you, sir.
No problem. Okay, so that's all for today. Have fun. You realize that this week has no lab sessions, but please go and look. Please go and do your R because we need your R for subsequent stuff. Okay. Without using R, you'll find that you will die just doing non-parametric tests, which the last batch pretty much killed themselves. Okay, you should see how stressed they are during exam. Okay, so yes, that's all for today. Okay, that's all. We're seriously. Bye bye.
Yes, sir. Thank you, sir. Thank you, sir.
Bye bye.